So I'll start with number 3. The first order decomposition of N2O at 1000 Kelvin has a rate constant. So let's look at this sentence. So we start with this sentence. The most important thing to notice is this is the temperature. It's not K. K is this thing. And if you get lost in the sentence, you might not notice that it says has a rate constant of blank at the end. This temperature actually never gets plugged in when you're doing the solution. If you look at Dr. Spencer's solution right here. The reason the temperature is significant is it makes the rate constant what it is, but you never plug it in anywhere. Now, if there were a question that said, how will the rate constant change if that temperature goes up to 5 million, then yes, the rate constant will go up. Anyway, if the initial concentration is so-and-so, so you just use normal equation for first order. The way you know it's first order is, it says first order. Also, the rate constant is seconds to the negative 1. So using this equation, you plug in what you know, what you don't know. The algebra, I'll show it. The algebra, the way she shows it, is quite straightforward, but let's say you know the other integrated rate law, which would be ln of A equals ln of A naught plus minus kt. So if you are starting from this point, then you do the, you know everything on the right side. So you do this, and on the right side, you can just simplify all that to a number, which is, so the right side is just a number. Natural log of stuff, you plug it in, you get a number. Then, here's the magic algebra step. You have to do e to the power of both sides. Now, you can just skip straight to this, or you can do the intermediate step, which would be e to the power of natural log of A equals e to the power of negative 4.91. And that intermediate step, the natural log and the e cancel out, and you get where we were before. It's acceptable to skip this highlighted intermediate step if you're comfortable jumping to it, but I prefer showing that step for my own, making sure I don't make a mistake. So, you plug that in, get an answer, which is 7.4, that. Now, number 4. Check the answer for that one. So, number 4. Answer the questions below based on the following equation. Yes. Equation. Graph. Write the rate law. Okay. For the rate law, we know that it looks like this. We know it looks something like this, but instead of A and X, you should really have something that's more appropriate to your problem. In this case, the reactant is, I'm not going to try to say the chemistry name of that. So for the X, this X is the order, and we can see that this is a linear graph with time on the x-axis. Natural log, hey, natural log, that's important. Usually natural log of the concentration on this, on the y-axis, and time on the x-axis. That if that's a line, then that tells us it's first order. So I could write to the power of 1, or just write nothing. That's usually the convention. Omit the 1. Now, what about that K? Do we know what K is? Yes, on the graph. This thing, right here, negative 0.0 blah, 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 without the T, is K. So this is K. The units, since it's first order, would be seconds to the power of -1. It's not shown here. By the way, this is the equation of this line, in case you were wondering what that's called. Y equals so-and-so times t, t being time. And that's the slope. K is negative the slope. K, so this is actually positive. Notice that I accidentally had a negative there. It is positive, not negative. That's what Dr. Spencer also has. She put it in scientific notation. So, the full rate law, if you want to include what K is, would be 2.90 times 10 to the -4. This. That's the rate law. Dr. Spencer wrote that. She just wrote K off to the side. But that's it. Here, I'll put units in here. And part B, half-life. Just use this equation. That's about it. Plug in the K you know, and you're done.